All right, we're going to go through this. If you notice, what I'm asking you to do in these problems is identify the electron geometry. So the electron geometry, I'll just write EG, okay, and the molecular shape. So I'll just write shape. And so these are two things that are slightly different, and I'll explain to you how. If you notice the problems, I just use the exact same problems that were in the previous video help. So we've already drawn out the Lewis dot structure, so that helps a lot. That's a first step in deciding the shape for electron geometry in the shape. Now, when we're considering electron geometry, what we're considering really is we're treating these lone pairs of electrons as if they were bonding pairs. Okay, so if we look, for example, I'm going to pull up this site online for you. Give me 1 second. There we go. All right, so here's my site, and the first thing I'm going to be looking at is H2S. So here's H2S for you, okay? And I'm going to rotate it around a little bit. If you notice, the gray dots are my hydrogens, the S is my sulfur. The blue spheres, those are my electron clouds. So there are 2 electrons here floating around, there are 2 electrons here. And remember, the reason why they do that, this is the VSEPR theory. The reason why they do that, they are repelling one another. So this is these locations where you see the gray dots and the blue circles, that is as far apart as they can be from one another. Now, if we're talking about the electron geometry of this shape, if you notice, if we consider these blue electron clouds, or the lone pairs, these are the lone pairs, to be bonding atoms, this is tetrahedral because you've got 4 things coming off of the central atom. You've got 1, 2, 3, 4. All right, so the electron geometry of H2S would be tetrahedral. So I'll go back here. The electron geometry is tetrahedral because we're considering the lone pairs of electrons as if they were bonding atoms. Tetrahedral. Now, for the molecular shape, we completely and totally ignore the lone pairs of electrons. So if we look at these again, sorry about that. If you ignore these guys right here and just look at the shape of the red circle with these 2 guys going off, it looks like it's almost trying to be linear, but it's not quite. And so if it's not quite linear, it's going to be bent. And just a trick, if you have electrons on the central atom, you will never have a linear shape. And we'll see when you do have a linear shape, but these electrons are forcing the hydrogen atoms downwards. So this shape, the molecular shape of H2S would be bent. All right, for Br2, I'm going to hit this. So the shape of this is going to be linear. Now, no, it does not have a double bond. I'm not sure in this program how to show it with just a single bond, but Br2, so Br2, you don't have a central atom, so you can kind of ignore this dot right here, and if you just consider these 2, we don't consider the lone pairs of electrons on the Br to be causing it to force downwards because Br doesn't have a central atom. So we're just going to be considering the magenta and the red balls right there, and so that's going to be linear. Now, in this case, the electron geometry and the molecular shape are going to be the same. They're both going to be linear. So that's a funky one because for most linear shapes that we consider, you've got a central atom and this is linear as well. You've got a central atom and then 2 things coming off of it. And if that's the case, then you will have what we just saw, which was this right here, where you have a double bond and a double bond. Otherwise, when you have this where you don't really have a central atom, it's still going to be linear. All right, for CO3, we've got this shape. So if you notice, ooh, so pretty. if you notice, you've got your central atom right here, and you've got 3 guys coming off of this. Notice that you don't have any lone pairs of electrons coming off of the carbon. And so as a result, since you don't have any lone pairs, your molecular shape is going to be the same as your electron geometry. So this one, functionally, this shape, for some reason I can't find one that shows a double bond. This should have a double bond right here. But since you don't have a lone pair, it's going to be trigonal planar for both the electron geometry and the shape. Trigonal planar. Now, so for both of them, so I'll just go like that. Now, a better example for the next one, if you look right here, if you notice, we've got 1 lone pair of electrons and we've got 3 bonding atoms. And if you look, this light blue is the lone pair of electrons, and what it does is it forces down the gray atoms. And the whole point of VSEPR theory is the fact that your atoms and your lone pairs of electrons are going to be as far apart from each other as possible. And so that's what they're doing. This shape is pyramidal. It looks like a little pyramid. But interestingly, if we consider the electron geometry, and in electron geometry, you have to consider the lone pairs of electrons as another thing coming up, the shape is actually going to be tetrahedral for the electron geometry. It's going to look more like that. So if we consider, in the last one, this was the lone pair of electrons, if we consider it to be another bonding atom, then it's going to be tetrahedral. So the electron geometry of NH3 is tetrahedral. I'm just going to write tet because I'm a little bit lazy. But then if you go back and look at the pyramidal, this right here, this shape, this is pyramidal. That is the molecular shape of it. So while if you consider the lone pairs of electrons, it's considered to be tetrahedral. If you don't consider them and just consider the atoms that exist, it would be pyramidal. Okay? And that is all.